I'm Kelsie Lam, a research intern at the SciTech lab, and today I'll be going over my mass detection workflow, which is a project I've worked on for a while now since the summer. Here is an overview of what I'll be covering in this video. First, I'll be going over Pegasus, and then my project goals, each machine learning workflow step, and I'll be wrapping it up with a summary of my internship. So first off, what exactly is Pegasus? Pegasus is an open source workflow management system developed in 2001 by USC research professor Ava Dielman. It uses a varied set of technologies to help workflow-based applications execute in a wide variety of scientific domains, such as astronomy, bioinformatics, gravitational wave physics, earthquake science, and much more. For example, Pegasus is used by the Southern California Earthquake Center to develop the CyberShake workflow, which is able to create a probabilistic seismic hazard map of Southern California. And on the right here is a diagram of the CyberShake workflow. Now I'll be going over my project goals with this mass detection workflow. So this is an important workflow, especially today with COVID-19 and CDC's encouragement to wear masks to help slow the spread. And in order to find out what percentage of a certain population is following this guideline, we can set up a camera to take pictures of people at crowded and public places periodically, and then run these images into the workflow to identify if people are actually wearing their mask or not. And since there are a lot of images that will come through, this workflow will make it very simple to do all of the steps and then reuse it periodically, as well as run multiple images in parallel. And also with the help of Pegasus, it can find the most efficient way to use all the computer sources available. Here is a simple overview of each of the steps. We start off with data acquisition and then data split, data pre-processing, hyperparameter optimization, and then we have model training, evaluate the model, and inference. Now I will walk you through each step individually. And at the top here is a simple flowchart of all of the steps, specifically which one I am going over at the moment. So as you can see, our first step is data acquisition. And in this step, we basically just get our data. So I downloaded the data from an open source on Kaggle, and this data set has a variety of images of people either wearing a mask, not wearing a mask, or wearing their mask incorrectly. And then once we have our data, we add it to the replica catalog, which just tells Pegasus where to find each of the input files needed. And at the bottom here is a snippet of the code we wrote where we added the image files to the replica catalog. And once we have our data, we can learn about the distribution of classes by adding the distribution plot job. And as a result of this job, our output is this graph here. And as you can see from this graph, our data is extremely unbalanced. We have a lot more images of people wearing a mask compared to images of people not wearing a mask or wearing their mask incorrectly. And so we have to account for this later on when we look at the final results of this workflow. Now, to perform a statistically sound experiment, we split our data into three categories: 70% training, 10% validation, and then 20% for testing. And by doing so, we can verify how well our model is performing by training the model on the training set and then verifying its performance on the test set. And then with the validation set, we use it to tune hyperparameters and avoid overfitting, which I will go into more detail later on. And as you can see at the top here, our next step is data pre-processing. So it is extremely crucial that we split our data before the pre-processing step to avoid data leakage, since there are some normalization steps that cannot be done on both the testing and training data. Now, since data comes from all sorts of sources, and in order to make them all uniform and consistent, we have to convert the data to a common format. And we can do so by adding jobs to standardize the data. And in data standardization, we basically just rescale the data so they all have a mean of 0 and standard deviation of 1. And in addition to that, we also added Gaussian noise, which alters the pixels and allows the images to become more robust so that we can increase the number of training images to use. So as you can see on the right, the image at the top is the original image without any Gaussian noise. And then the image at the bottom is the same image, but with the Gaussian noise. Next is hyperparameter optimization. And in this step, we use Optuna. Optuna is a automatic hyperparameter optimization software framework for machine learning. And with Optuna, we can create a study to find the best parameters. And then with this proposed set of hyperparameters, we can implement it into our model. So in model training, the model we used is a pre-trained model called FastRCNNPredictor. So this model is already good at finding faces. So we just fine-tuned it so it is better at classifying the faces and then putting it into the 3 different categories. And at the bottom here is a step-by-step diagram of this model. The first step is to give the model our image, and then it will extract region proposals or ROIs, regions of interest. So basically, it just takes only the needed portions of each image. So in our case, it will just be the areas of a person's face. And then once it has that, it will, at the end, it will categorize the face into one of the 3 groups, either with mask, without mask, or mask worn incorrectly. So now we evaluate the model by looking at the loss curves as shown in the graph at the bottom to see if the model overfits or not. And overfitting is basically when it follows too closely to the training images. So basically it just memorizes a certain pattern instead of being able to generalize to new images. And as I mentioned before, our data is pretty unbalanced. So in our case, a confusion matrix will be the most helpful because it can give us the exact cause of error. So it will tell us if it's either a true positive, false negative, or true negative. Now we can also evaluate our model by looking at the output image. So in these 2 images, the green boxes are the true labels and the red boxes is what the model predicts. So as you can see, the model does a fairly good job, except for on the left, it forgot to detect someone's face here. And then on the right, it added a bounding box when there actually wasn't any face present. Lastly, in the inference step, we can use our own images. So we gathered image pictures from the members of the Pegasus team to see how well the model would run with these images. And by looking at this, we can see that it does a great job detecting people wearing their mask correctly, since the confidence level is pretty high at 99.09%, and even as high as 99.55%. So it does a great job classifying people wearing their mask correctly. However, we can also see what areas we need to improve on, such as balancing out our data and adding more images of people wearing their mask incorrectly, because the confidence level here is a lot lower, 16.31% and even as low as 5.31%. So that is one thing that we can improve on. Another thing is diversifying our data set. So at the top here in Wendy's group, you can see that it detects the hat as another face. And this is because the model isn't used to seeing head coverings. So if we diversified our data and added more head coverings and also balanced out our data set, it could our results will be a lot more accurate. Now I'll be going over a summary of my internship. So I definitely learned so much during this experience. I first started the internship with very, very minimal coding experience, but through this workflow and writing various scripts, I've definitely enhanced my coding skills, especially in Python. And I've also developed a greater understanding of machine learning. At the beginning of my internship, I would read articles and papers of scientists and their projects. But now that I can actually create my own, I've learned a lot more, such as using Optuna and the various Pegasus features, such as Docker and checkpointing, that make it a lot more efficient and easy for scientists to work and share their ideas. Additionally, I've also been able to utilize GitHub, such as pushing and pulling any changes made. And I've also had the opportunity to collaborate with so many wonderful people on the team, like Patricia, Shrujana, and Shubham. So, moving on to my acknowledgments, I want to thank everyone in the machine learning group for being so amazing, kind, and helpful to me whenever I needed help or ran into any issue. And I also wanted to give a special thank you to Professor Dealman, Patricia, and Ryan for teaching me so much, always being there for me, and just giving me this amazing opportunity to learn from you guys. And yeah, thank you so much.